Our epic odyssey begins on the surface, where sweat glistens like liquid jewels against the pores of the skin, a silent witness to the immense physical toll demanding its share of energy. This is the signal, the call to summon the strategic reserves buried deep within. We plunge now through the surface of a single sweat drop, a microscopic aquatic world reflecting the sun's glare, and dive boldly into the crater of a skin pore. Here, the roar of the outside world fades into a distant whisper, and the familiar laws of physics begin to dissolve. Descending through the tunnel of a hair follicle, we witness layers of keratin stacked like ancient stone shields guarding the gates. A subtle rise in temperature greets us, a thermal signature of the fires burning in the strata below. We weave through the tightly packed layers of the epidermis, where cells lock together like an unbreakable fortress. Between the microscopic crevices, interstitial fluids shimmer under the weight of osmotic pressure, paving our way toward the most vibrant and active layer of all. We have arrived at the dermis, a dense forest of collagen fibers, stretching like the roots of giant, intertwined trees, granting the skin its resilience and strength. Subtle currents of fluid move in harmony with the distant, rhythmic thrum of a beating heart. We navigate carefully through the elastic networks of elastin that snap back with the force of rubber, a testament to the tissue's vitality, while a faint mist of organic molecules floats in the interstitial space, carrying cryptic chemical dispatches. Before us surges a great river of life, a delicate capillary vessel where red blood cells rush at breathtaking speeds, ferrying oxygen like the essential fuel needed to ignite the fat-burning fuse we've come to witness. Following this crimson conduit downward, the landscape shifts. The white collagen fibers vanish, replaced by golden yellow masses looming on the horizon like a dominant entity in these depths. We are now crossing the frontier into the subcutaneous tissue. The laws change here. The environment becomes denser, more viscous. This is the body's greatest treasury, the world of the adipocytes. It is a majestic sight. Millions of fat cells clustered like giant clusters of grapes, each one a biological vault, overflowing with frozen chemical energy, awaiting the order to be spent. We draw closer to a specific fatty lobule, encased in a thin veil of connective tissue that holds these cells in a precise organizational unit. The faint echo of lymphatic fluid washing over this cellular colony resonates around us. Notice how the capillaries embrace the surface of these cells, a complex web of red pipes wrapping around every adipocyte to ensure hormonal commands are delivered and the byproducts of the coming reactions are swept away. In the narrow gap between the blood vessel and the fat cell wall, a rich interstitial fluid teems with proteins and ions, a crowded environment buzzing with constant molecular motion. Within the nearby bloodstream, tiny messengers swim chemical distress signals, the adrenaline hormones released in response to exertion, rushing like an army of couriers toward their destination. We watch a critical moment as adrenaline molecules leak through microscopic gaps in the capillary walls, moving from the rushing torrent of blood into the quiet tissue fluid surrounding the cells. These hormonal molecules move by diffusion now, drawn like magnets toward their giant targets, those fatty fortresses looming like yellow planets in a dark space. As we move closer, a single fat cell fills our entire field of vision, a massive sphere nearly bursting with its load, covered by a thin biological membrane that separates its inner world from the external chaos. The surface is not smooth. It is a rolling terrain of phospholipids, a sea of polar heads swaying and dancing in an eternal chemical symphony. Upon this undulating surface, complex protein structures rise like watchtowers. These are the beta-adrenergic receptors, the sentinels waiting for the password to begin the deconstruction. This receptor is a masterpiece of nanoengineering, consisting of 7 helices that pierce the cellular membrane, forming a vital bridge between the outside world and the sleeping machinery deep within. An adrenaline molecule approaches slowly, guided by electrostatic forces, like a spacecraft attempting to dock with an orbital station. The decisive moment is here. With surgical precision, the molecule settles into its designated slot on the receptor. An electromagnetic shiver ripples through the membrane, signaling a successful connection and the start of an irreversible chain of events. Upon docking, the receptor undergoes a conformational change, a precise mechanical twist at the atomic level that releases latent energy toward the inner side of the membrane. We move now to the opposite side, inside the cell, where the receptor's tail moves like a mechanical arm, searching for its partner in this biochemical dance. The receptor touches the G protein GPROTEIN, crouching nearby, awakening this sleeping giant. It discards a GDP molecule to bind with a high-energy GTP, now primed for action. The alpha subunit of the G protein breaks away, sliding rapidly across the inner surface of the membrane, like a master skater cutting through ice, heading toward its next target in this meticulous sequence. The alpha subunit reaches a pivotal membrane-bound enzyme called adenylate cyclase and locks onto it firmly, powering up this molecular factory to its maximum capacity. The enzyme begins work instantly, pulling in surrounding ATP molecules, twisting and reshaping them into tiny secondary messenger molecules known as CAMP, which scatter like magical dust. Dense clouds of CAMP diffuse into the cytoplasm, carrying a general mobilization call to every corner of the cell. This is the signal language the internal machinery understands perfectly. We take a wide look at the cytoplasm and find it to be a narrow, crowded strip squeezed between the outer membrane and the massive central lipid droplet that occupies nearly the entire volume of the cell. In this crowded space, we see protein kinase, A units P, K, A, in a state of dormancy, shackled by regulatory units that prevent them from exercising their bond-destroying activity. But soon, the CAMP molecules arrive and assault the regulatory units, binding to them and forcing them to release their grip. The catalytic units of the enzyme are liberated, surging forth, free and untethered. The freed PKA units transform into highly active machines, glowing with chemical energy as they swim through the cytoplasm, hunting for specific targets to phosphorylate. In the background, the central lipid droplet looms like a giant planet, a massive reservoir of triglycerides protected by a protein coating that prevents any digestive enzyme from reaching it. Approaching the surface of this fatty planet, we discover it is not bare, but covered in a complex protein sheath, a great wall called perilipin that guards the treasure within. Perilipin molecules shake hands and interlock like the shields of a Roman legion, forming a physical barrier that prevents any fat-dissolving enzyme from nearing the stored triglycerides. We also notice a small protein called CGI-58, held captive and bound by the perilipin, like a prisoner of war waiting for the moment of freedom to play its vital role in the breakdown. Now, the battalions of active pKa enzymes reach the borders of the lipid droplet and launch a precise chemical assault on the protective proteins. Armed with phosphate groups, the pKa glues charged phosphate groups onto the surface of the perilipin. This phosphorylation process is like planting explosive charges that alter the physical properties of the protective wall. Under the weight of these new charges, the perilipin twists and deforms, creating gaps and fissures in the shield, exposing part of the fatty surface beneath for the first time. As a result of this distortion, perilipin loses its ability to hold CGI-58. The helper protein breaks free, swimming into the surrounding cytoplasm in search of its partner. CGI-58 quickly finds a massive and relatively dormant enzyme called ATGL, adipose triglyceride lipase, and docks with it, activating the enzyme and increasing its efficiency hundreds of times over. The newly activated ATGL complex moves confidently toward the gaps in the perilipin wall, ready to deliver the first blow in the fat-cracking process. We peer into the breach and see triglyceride molecules packed together, each consisting of a glycerol backbone and 3 long fatty acid tails, swaying slowly. ATGL positions itself over a triglyceride molecule, adjusting its stance with surgical precision to target the first bond holding one of the fatty acid tails. Using a water molecule as a cutting tool, ATGL ATGL launches its attack, snapping the ester bond with force, separating the first fatty acid from the main structure. The first fatty acid detaches and swims away like a liberated thread, while the remainder of the molecule becomes a diglyceride, a less stable compound. Elsewhere in the cytoplasm, pKa enzymes are still at work, now activating another crucial enzyme, HSL, preparing it for the second stage of the assault. HSL changes its shape to reveal its active site and migrates across the cytoplasm toward the lipid droplet surface, taking advantage of the openings made by the phosphorylated pyrrolipin. HSL arrives at the battlefield and targets the remains of the previous molecule, the diglyceride, grasping it with powerful molecular claws to prevent its escape. With a decisive chemical strike, HSL severs the second fatty acid, freeing it to join its brother and leaving behind a lonely, battered molecule called a monoglyceride. Chaos intensifies at the edge of the droplet as free fatty acids and monoglycerides accumulate, creating osmotic and chemical pressure that drives the next step. Now comes the final cleaner, the MGL enzyme, which requires little stimulation. It is present in abundance and pounces on the remaining monoglyceride molecules. MGL cuts the final bond, completely separating the glycerol from the third fatty acid. The triglyceride structure is officially finished, vanishing entirely. What was once a cohesive molecule is now scattered parts. 3 free fatty acids and 1 glycerol molecule, all swimming in the cytoplasm, ready to depart. The fatty acids now face a grueling journey through the watery cytoplasm, which their oily nature detests. They require special transport proteins to smuggle them toward the membrane. FABP proteins intercept these fatty acids and embrace them, forming a protective shield that allows them to glide through the cell's aqueous environment without clumping or sticking. The energy-laden caravan reaches the cell's plasma membrane from the inside, preparing to cross the final gate into the vast outside world. Through a complex mechanism, the fatty acids and glycerol cross the membrane's bilayer, bidding farewell to the cell that was their home and emerging into the interstitial space. Glycerol, being easily water-soluble, slips like lightning through the microscopic pores of the capillaries, dissolving into the plasma to begin its own journey. The fatty acids, however, face a problem. Blood is a watery fluid, and they are oils that do not mix. They stand at the edge of the blood vessel, waiting for a safe means of transport. Here, the giant albumin proteins loom on the horizon, white cargo ships patrolling the blood, equipped with special pockets designed specifically to receive and transport fats. The fatty acids leap into the albumin pockets, each protein carrying several molecules, transforming into a mobile energy reservoir, swimming with the blood current. These loaded ships now race through the venous bloodstream, moving away from the adipose tissue and heading toward the heart to be pumped to the muscles in need. We pass through the pounding valves of the heart, where the powerful muscle pumps us with immense force, driving the oxygenated blood, laden with fatty fuel, to all corners of the body. We finally reach our destination, a delicate capillary infiltrating the muscle tissue of the thigh, where the demand for energy is at its peak and the work never stops. At this station, the fatty acids detach from the albumin and leave the bloodstream to cross into the fuel-hungry muscle cell. Inside the muscle cell, we see thousands of mitochondria, oval-shaped power plants, buzzing with activity, preparing to receive the new fuel shipment. The cell utilizes a specialized transport system called the carnitine shuttle to smuggle the fatty acids across the double membranes of the mitochondria into the heart of the furnace. Inside, the process of beta oxidation begins, where the long carbon chains of the fatty acids are chopped into small units of acetyl-CoA. The acetyl-CoA units enter the Krebs cycle, a vortex of chemical reactions that strips high-energy electrons from the carbon. These electrons flow through the electron transport chain, generating a microscopic electric current that pumps protons and creates a massive potential difference across the inner membrane. The torrent of protons rushes back through the ATP synthase turbine, spinning it at an unbelievable speed, fusing phosphate and generating the universal energy currency of life. Fresh ATP molecules shoot out like bullets, heading toward the actin and myosin fibers in the muscle to grant them the power to contract and move. We see the myosin heads consuming ATP P, to pull the actin filaments, causing the muscle fiber to contract and generate mechanical force. As a result of this clean combustion, the mitochondria produce CO2, carbon dioxide, and water, the remnants of the process of turning matter into energy and motion. The CO2 gas leaks back into the blood to be transported away toward the lungs, completing the eternal cycle of gas exchange. Not all energy turns into motion. Some of it escapes as microscopic heat waves spreading to warm the surrounding tissue and maintain body temperature. We begin to pull back from the molecular level to see millions of muscle fibers working in stunning symphonic harmony, driven by that energy derived from fat. The leg muscles are seen contracting and relaxing under the skin, a mighty biological engine, translating chemistry into physics and stored fat into speed. We return to see the runner in full. He exhales forcefully, and that cloud exiting his mouth is not just air, it is the carbon atoms that were once part of the fat in his body. In this exhalation, we see the poetic end of fat, where heavy physical mass transforms into light, gas, and water vapor, vanishing into the ether, leaving behind only energy. It is not just exercise, it is a cosmic transformation. Man burns his past, stored in his cells, to create his kinetic future in this very moment. A halo of heat and energy surrounds the body, the product of trillions of microscopic reactions we have just witnessed, dancing around him like an invisible shield of life. And so, the journey continues. Every step this human takes is the final sum of a great chemical epic that unfolded in secret within the smallest living units. Let us remember for a moment that thin membrane, the barrier separating existence from nothingness, and appreciate the brilliance of the design that allows all this exchange. The proteins we saw are not inanimate objects. They are microscopic mechanical beings, folding and unfolding with a precision that exceeds the most complex Swiss watches. Those carbon atoms, forming the fatty backbone, are ancient solar storehouses, holding the energy of light for years, only to release it now. Even water, that simple component, plays a starring role. It is the solvent, the carrier, and the participant in hydrolysis, the lifeblood of all these processes. As the fat leaves, the adipocyte shrinks slightly, lightening its load and returning to a state of relative stability, waiting for the next meal or the next round of burning. The energy cycle never stops. The ADP, resulting from muscle consumption, returns to be recharged once more in an eternal cycle of chemical death and rebirth. The blood network connecting fat stores to muscle engines is the highway that ensures the organism remains capable of responding to challenges. And let us not forget the role of the nervous system, sending its electrical signals in parallel with the hormones, a maestro leading the orchestra to ensure perfect synchronization. The specificity of enzymes is the secret of life. If a single enzyme failed to recognize its target, the entire system would collapse into utter chaos. Muscle tissues glow red and orange in thermal imaging, a sign of the efficiency of the biological furnace, turning matter into energy. While all this noise occurs, the nucleus of the fat cell sits in the corner, watching silently, controlling the production of more enzymes to replace what was consumed. The genetic code within the nucleus contains the engineering blueprints for every protein we saw, a cosmic library preserved in a space that barely exists. RNA messages exit the nucleus as construction orders, heading to the ribosome factories to rebuild the soldiers of the battle from enzymes and proteins. We witness now the birth of new enzymes, as ribosomes link amino acids with precision, preparing the cell for a future round of fat breakdown. In this small world, the random motion of molecules is the primary driver, a creative chaos, ensuring that reactants meet one another at the right time. As the effort continues or ceases, adrenaline levels begin to drop, signaling the cell to start slowing down the combat operations. Adrenaline molecules detach from the receptors, and the receptors return to their dormant state, cutting the signal that was igniting the reaction. Inhibitory enzymes, phosphodiesterase, appear to clean the field, breaking down the remaining CAMP molecules to end the state of emergency within the cell. pKa units return to bind with their regulatory units. The fires of enzymatic activity die down, and the phosphorylation of perilipin gradually stops. The perilipin wall reshapes itself, closing the gaps and returning to be that impenetrable shield protecting the remaining fat stores. C.G.I. -58 is recaptured and placed under house arrest once more, stopping the stimulation of the A.T.G.L enzyme, and calm returns to the surface of the droplet. The ripples of the cell membrane subside, and the cell regains its internal balance, as if the storm that swept through it moments ago was nothing but a passing dream. Outside, the tissue fluid returns to its usual clarity, and the capillaries continue their routine cycle, but now they carry fewer wastes and fewer hormones. Insulin molecules may appear on the horizon, messengers of peace and building, to start a completely opposite cycle, the cycle of storage and repair instead of burning and destruction. It is the delicate balance between lipolysis and lipogenesis, the continuous dance of life between catabolism and anabolism that ensures the survival of the organism. We ascend back toward the surface, where we see the skin cooling gradually. Sweat evaporates, leaving behind fine salts, evidence of the thermal battle that has ended. Surface capillaries constrict slightly to preserve the remaining heat, and blood circulation returns to its normal distribution in a state of rest. The runner's body stops its violent movement, and his breath slows, but the cells in the depths never stop. They simply switch from one mode to another. Every quiet breath now is a continuation of the oxidation process, a slow, sustainable burning of fat to maintain essential, vital functions during rest. In the alveoli, oxygen still flows to meet the blood, the indispensable partner for any future fat-burning process. Chemical signals of satisfaction reach the brain. The body has performed its function, and stored resources have been utilized efficiently to ensure survival and evolution. We see the human now not as a mass of flesh and bone, but as a flame of light energy, glowing and fading based on its internal microscopic interactions. If we sped up time, we would see how fat stores shrink, day after day, with continued effort, a tangible physical response to the mind's decision of will. This journey proves to us that the body is one indivisible unit. A decision to move in the brain moves a molecule in the deepest fat cell in the foot. As we move away from this small body toward space, we realize that the laws of energy governing that fat cell are the same laws governing stars and galaxies, one single symphony of existence.